Hey, hello. It's me again. Uh, just make it this a little bit thicker. Okay. So when you have a circuit like this circuit here, so you have a voltage and you have something like a 200 ohms 200 ohms resistor, and then you have a light bulb, right? Go in there. So basically what you expect is to have a current that goes down and then do something here in this 200 ohms resistor, light up your light bulb, go back to the power supply, and that's it. So let's say you want to check the voltage and make sure the voltage is correct, right? So, and sometimes you found that's the situation we do. We have a voltmeter and we want to make sure the voltage that is being read is correct. So we have our ground here, and you have a terminal to read voltage, and then what do, you plug a cable in here, and you have another cable, and you have another cable that goes right here. Okay, so this is black. So you remember this, right? And then we read certain voltage. But is exactly what you're doing here is creating and putting this guy in parallel. So this is pretty much parallel with your circuit, which means when, and I will redesign this circuit here. So here is your resistor, light bulb, back there, and then here is, this is an outlet for your voltmeter, and this is an outlet to your voltmeter. So basically, when the current comes out here, see, it reached this junction, and then it splits in one current I1 and one current I2, so that the current that is reaching this junction here, let me put in a different color, right here. So you want this current I be equal to I1 plus I2. Like you have a certain amount of water going through a T junction, and then you divide some of the flow here, some of the flow there. Well, when you plug this voltmeter in your circuit, you want this current here, I2, to be as small as possible. In other words, you want I1 to be as close as possible to I. You don't want to alter that much the circuit. So how that's done? So the way we do is voltmeters, they have very large internal resistance. For instance, the vernier internal resistance is about 20 mega ohms, if I'm not mistaken. So it's a kind of a big one. Okay, so that's the idea. But in your voltmeter, in addition to this mega resistance, you have something called a galvanometer. So a galvanometer, reminding me to show you in the lab, is a little device that when you input a small current, so you want an I2, remember, to be small, when it goes with a small current, and then this small current causes a deflection of a dial because current creates magnetic fields, as we are learning, and that is enough to generate. And I show in designs in the lab how that works. So, and then you can calibrate your galvanometer to read between, let's say, between a range of current. It's going to be giving you some reading in the dial, and then you calibrate that dial to whatever you want. In this case, our voltmeter has different ranges of voltage it can read. So basically, depending on the amount of current that goes inside, you can read the voltage, which is proportional to it. So going now to the exercise itself, which is this one over here. So these two, what did I do? I just burned the galvanometer. Yeah, so why did I burn the galvanometer? Because I have a battery of voltage 2, right? And the resistance is 200, so let's calculate that. So if I have a power supply that fits 2 voltage, and I have a resistance of 200 ohms, and I have a galvanometer here, and I have a galvanometer that is 0.2 ohms back to the power supply. So this galvanometer cannot read more than, what's the current? I think 0.6. 1 microamps. So maximum current here is 1 microamps. So the current that goes in here cannot be larger than that. But what is the current? Well, we know, we use Ohm's law, V is equal Ri. So 2 is equal 200 plus 0.2 times the current. The current is equal to divided by 200.2, and then we have a current that is, what is the calculator? We calculate that. There you go. So 2 divided by 200.2. So the current is equal to 0.0099, and that is equal to 9.9 microamps, which is much larger than 1 microamps. So that's why that thing burned, right? So if you wanna the current here to have a maximum value of 1 microamps, right? So what should be the internal resistance of this resistor? So let's do it again. So we have a resistance that you don't know what it is. You know your galvanometer has an internal resistance of 0.2, and you wanted the maximum current, because if you go more than that, you're going to burn to be this much, and the voltage is 2. So what would be? You apply Ohm's law. 2 volts is equal to R, which you want to find, plus 0.2, which is fixed, times 10 to minus 6. That's the current, amps. So R plus 0.2 is equal to divided by 10.6, which is 2 mega ohms. So the resistance should be 2 mega ohms minus 0.2, right? So you know the resistance is pretty much close to 2 mega ohms. That's the idea. Okay. So I hope that clarified this this exercise. And when we are reading current, when we read current, as you know by now, so you have, let's say, a circuit like this, and you have a resistance. Oops, what happened? And you have a resistance, and you have a light bulb, and you want to read the current that's flowing through the circuit. So what do? You break the circuit somewhere, and then you draw this to your meter that comes out and back there, right? That's basically the difference between ammeters and galvanometers. So with the ammeter, what exactly you have? Well, you have a galvanometer again, so you have a galvanometer in there that has a very small resistance, internal resistance. And the resistance has to be much less than those over here, so that if we include a internal resistance, or so if you take your circuit by replacing with your meter, you are essentially adding a internal resistance that's much less than R, which is this R over here, or this R, right? Much less than those quantities. Then you are not altering the characteristics of your circuit.